Hello students, this video lecture will cover section 9.4 Symmetry. The learning goal for this lesson is to identify the type of symmetry in a figure. So first, some vocabulary. A figure has symmetry if there is an isometry that maps the figure onto itself. Remember, isometries are transformations that maintain congruency of the figure. So there are different types of symmetry. We say that a figure has line symmetry, or most frequently referred to as reflectional symmetry, if there is a line of reflection for which the figure is its own image. The line of reflection is called a line of symmetry, and it divides the figure into two congruent halves. So we can see that with this isosceles trapezoid, if we were to fold the figure right on this dotted line, this half of the figure would line up exactly over this half of the figure. So that's reflectional symmetry. A figure has rotational symmetry if there is a rotation of 180 degrees or less for which the figure is its own image. The angle of rotation for rotational symmetry is the smallest angle needed for the figure to rotate onto itself. So in this example, we have an equilateral triangle. You can see that if you take this location and rotate it 120 degrees to the left, or counterclockwise, we would have the exact same figure. And a figure with 180 degree rotational symmetry also has point symmetry. So this is a special title given to 180 degree rotational symmetry. And so each segment joining a point and its 180 degree rotation image passes through the center of rotation. And so a square, which has both 90 degree and 180 degree rotational symmetry, also has this special type of symmetry called point symmetry. So let's look at question number 1, identifying lines of symmetry. So we're trying to determine how many lines of symmetry a regular hexagon has. Okay, so first things first, if we were to draw a dotted line directly down the center of the figure, and we fold this figure over onto itself, it would certainly overlap perfectly. So we can see that this definitely has at least this type of reflectional symmetry. Now, in addition to this, these same types of symmetry occur on these alternate angles. So you can see by turning your head slightly to the left or right that it also reflects across these lines. Now, in addition to these lines of symmetry, we could also draw directly through the vertices. So in this case, we would have this trapezoid over here that would fold over onto itself. So we can draw lines through all of the vertices of this hexagon as well. So there are certainly lots of lines of symmetry that a regular hexagon has. The mistake that people make is usually counting them incorrectly. So you can see that this orange line is one all by itself. So if we start counting, we have this one, we have this one, we have 3, 4, 5, and 6. Now the mistake that I see people making is they count this one as 7. But if we follow this one to the other side, we can see that we've already counted it. And the same thing with all the rest of these. So how many lines of symmetry does a regular hexagon have? It has 6 lines of symmetry. So then we get into different figures. So let's take a look at a rectangle. So here we've included a rectangle that is not a square on the slide. Now certainly we can cut this rectangle both horizontally and vertically with no issue. The problem with rectangles is when we attempt to cut across the diagonal. Now if I were to cut this across the diagonal and try to fold this directly over, you can see that we would get something that is not really what we're looking for as line symmetry. This point right here reflected across this line would end up somewhere over here. And this point is not on the figure, so this is not a line of symmetry. So when we're talking about rectangles specifically, rectangles have 2 lines of symmetry. We have the vertical line of symmetry, And we have the horizontal line of symmetry. There are no diagonal lines of symmetry in a rectangle. So as a median of a triangle, line of symmetry for the triangle, and explain. So generally the first triangle that people draw is they draw an equilateral triangle. That's the first triangle that most geometry students have come to mind. And so then the median is the point at which the vertex of the triangle meets the opposite side in the exact middle. So we have these two segments which are exactly the same. Now, in the event of an equilateral triangle, the answer to this question is certainly yes. Because you can see if I took this piece and folded it over, then it would certainly line up over itself. And if I take this line and I move it so that it goes through a different vertex, you can see that this piece would also still fold over onto itself. So not only is it yes, it's yes for all three. Now things get a little bit different once we start talking about different types of triangles. Here we have an isosceles triangle, so if I draw the median of this triangle, you can see that what I'm looking for is the line that connects a vertex to the midpoint of the opposite side. So if I draw this median in this triangle, then of course in at least one of them the answer is yes. The problem that we run into is once we try to draw either of the other two medians. So you can see once I get over here and I'm connecting this vertex to this midpoint, the triangle would certainly not fold over to itself. So in an isosceles triangle, the answer is yes for just one. And if you check in a scalene triangle, the answer is going to be no. No line of symmetry is a median in a scalene triangle. In fact, scalene triangles have no lines of symmetry. So rotational symmetry. We're asked, does the figure have rotational symmetry? If so, what is the angle of rotation? Well, the first thing that I'm going to do is I'm going to recreate these figures. So here I've recreated the triangle and I'm going to try and rotate it 180 degrees or less and have it look exactly the same as it is now. You can see that no time in 180 degrees does this triangle ever look the same as it does in black. So this figure does not have rotational symmetry. So now I've recreated the star, and as I start to rotate it, you'll see that very quickly the star becomes the same as it was. Now the question exists, how many points are going to line up exactly, and so what then is the angle of rotation here? So you can see if we were to mark the center, the points are what first strikes me as coming together. So this point was over here. It's rotated into place again. So you'll see that there are 1, 2, 3, 4, 5 points on this star. So the angle of rotation is going to come from taking 360 and dividing it by 5. And so as you can see, this does in fact have rotational symmetry, and it's a 72-degree angle of rotational symmetry. And so here we have this final question. As we start to rotate it, we can see that after an exact 180-degree rotation, it ends up right back onto itself. So every 180 degrees, the figure overlaps exactly. So the answer to this question is going to be yes also, and this is 180-degree rotational symmetry. And remember, there's a special title when it's 180-degree rotational symmetry. This actually has point symmetry. The three-dimensional objects can also have the various types of symmetry. They can have reflectional symmetry in a plane and rotational symmetry about a line. So here we can see that this cube, a plane that cuts it horizontally through the middle, is going to create two congruent halves. And if you draw the center line of a cylinder, we can rotate it around, and every single image of any angle is going to be the same as the pre-image. So if we identify symmetry in 3 dimensions, we're looking at some of these specific objects. With this bowl, if you were to picture it from above, you could cut it exactly in half from above and have 2 pieces that were exactly the same. So this certainly has reflectional symmetry. In addition to that, if we take the bowl and draw a line through the exact center, any angle of rotation of a circular object is going to give us rotational symmetry. So this bowl has both reflectional and rotational. Now the pitcher actually has kind of a different shape. It's not perfectly spherical in all locations. So if we were to try to draw this, we have kind of the mouth of the pitcher, then we get this round piece around it, and then in addition to that, there's the handle. So certainly there is one plane with which we could cut it and we would get 2 pieces that were exactly the same. So this does have reflectional symmetry. However, the pitcher does not have rotational symmetry. The only way we could rotate this to be exactly the same is if we spun it 360 degrees. And remember, for rotational symmetry, it has to be 180 degrees or less. And using the same logic that we used on the bowl, we can see that from above, this lamp would have both reflectional symmetry, and since it's circular at all levels, we would say that this also has rotational symmetry. So that concludes this video lecture on section 9.4 symmetry. Hopefully you're now able to identify the types of symmetry that a figure has. Thanks for your attention, and I'll see you soon.